Okay, we're going to go over to 16b now. It's a continuation of 16a. The title for this one is 16b Relativity Hyperbolas Neutrino Muon Einstein Kinetic Energy OPAL LEP CERN and Detector. I am on my last legs here for power, so hopefully we don't run out, or we'll be making a C video. Okay, so 16b is continuing the thoughts about the Einstein's relativity theory. The neutrinos and hyperbola comes up as well. So I'm going to be posting these links on the blog Victoria Stafford Psychic Investigation on WordPress. So I'm going to show you what the equation brought up. Superluminal neutrinos would wimp out en route. It says not so fast, say to theoretical physics. Actually, I'm going to read you that in this next thing. But I saw the word hyperbola, traveling faster than light, came up together, so I put it there. Sorry. Fundamentals of neutrino physics and astrophysics. The hyperbolas comes up again. And then I googled special relativity, Einstein's theory in relation to neutrino data from 2012, and makes this theory questionable now. They're now questioning this theory. SR, also known as the special theory of relativity, or STR, is the physical theory of measurement in an inertial frame of reference proposed in 1905 by Albert Einstein after the considerable and independent contributions of Hendrik Lorentz, Honoré Poincare, and others in the paper on the electrodynamics of moving bodies. It generalizes Galileo's principle of relativity, that all uniform motion is relative, and that there is no absolute and well-defined state of rest. No privileged reference frames from mechanics to all the laws of physics, including both the law of mechanics and of electrodynamics. Whatever they may be, special relativity incorporates the principle that the speed of light is the same for all inertial observers regardless of the state of motion of the source. So no matter how fast it is, it all relates to the speed of light. This theory has a wide range of consequences which have been experimentally verified, including counterintuitive ones such as length contraction, time dilation, and the relativity of simultaneity, contradicting the classical notion that the duration of the time interval between two events is equal for all observers. On the other hand, it introduces the space-time interval, which is invariant. Combined with other laws of physics, the two postulates of special relativity predict the equivalence of matter and energy, as expressed in the mass-energy equivalence formula E equals mc2 squared, where c is the speed of light in a vacuum. The predictions of special relativity agree well with Newtonian mechanics in their common realm of applicability, specifically in experiments in which all velocities are small compared with the speed of light. Special relativity reveals that c is not just the velocity of a certain phenomena, namely the propagation of electromagnetic radiation, which is light, but rather a fundamental feature of the way space and time are unified as space-time. One of the consequences of the theory is that it is possible for any particle that has rest mass to be accelerated to the speed of light. This is what they're questioning now, because according to these test results, January 2012, these neutrinos that they found, which are the smallest particle in the universe, are supposedly traveling faster than the speed of light. Well, they've actually made them. They've somehow made them travel faster than the speed of light. And they've tested it 3 or 4 times, and they're currently going through the testing trying to figure it out. So here again, we have something that's going on, something that's invented, but we don't know what we can use it for. Okay? I believe they can use it for this rocket engine that we need for this faster UFO to travel to other worlds. Now, based on this data that's coming up, that's what I'm thinking that they're trying to let us know. The theory was originally termed special because it applied to the principle of relativity only to the special case of inertial reference frames, i.e. frames of reference in uniform relative motion with respect to each other. The reason I'm reading a lot more than I normally do, I usually do only a few lines for the quotes, but in this case I didn't know anything about this, and this is really important because This is based on every single thing in our universe, all our measurements, the stars, the planet, everything is based on this. Anything to do with algebra, all that stuff, it all has to do with this development from Einstein. And if these neutrinos do in fact start traveling faster than the speed of light, and that is proven, then this theory is going to have to be changed and it's going to have to be rewritten. Okay? So Einstein developed general relativity to apply the principle in the more general case, that is, to any frame so as to handle general coordinate transformations. And that theory includes the effects of gravity. So now we have something that has to do with the effects of gravity. So this theory that he has something to do with gravity. And we also talked about space gravity before, right? In another video. Earlier video, before line 16b. The term is currently used more generally to refer to any case in which gravitation is not significant. General relativity is the generalization of special relativity to include gravitation. In general relativity, gravity is described using non-Euclidean geometry so that gravitational effects are represented by curvature of spacetime. Special relativity is restricted to flat spacetime. The reason I'm talking about this now is because with these asteroids and comets and stuff that fall by the Earth, and any planets that pass by us, their gravitation, especially if they're bigger than us, it pulls us towards them. So it can push Earth off its course. It can cause earthquakes and changes in the time. The last earthquake that was from Japan was caused. There was an asteroid that passed by Earth. It had quite a gravitational pull on it, and it moved the Earth 25 centimeters. Our noon, solar noon, which is usually at 12 noon, is now at 12:25. Our weather has changed. It's a difference of 25 degrees in temperature. Like, it's all 25, 25. The number 25 is changing all sorts of things all over the Earth. And now we also have what we call our heat wave going on up in the poles, North and South Pole. It's melting the ice. So it's going to cause our sea levels to rise. And if it continues, your sea levels are going to rise up to 297 feet according to the data that came up. So, okay, so that would tie in with the end of the world thing, December 21st, 2012. That could be one of the catastrophes. It's talking about flooding happening on the Earth. So, in general relativity, gravity is described using non-Euclidean geometry so that the gravitational effects are represented. Okay, just as the curvature of the Earth's surface is not noticeable in everyday life, that's why they used to think the Earth was flat, and they found out it was round afterwards. The curvature of space-time can be neglected on small scales so that locally special relativity is a valid approximation to general relativity. The presence of gravity becomes undetectable in a sufficiently small free-falling laboratory. Now, the Sudbury Observatory that was using neutrinos, that was doing some stuff with neutrinos, talks about a free-falling laboratory that they built to do the testing. So that's why I read that whole section there. Okay? So that's that. I don't think there's any more. Oh, what do I know, right? All my notes have been moved around. I was rearranging them and I forgot to move the rest of them over. Okay, sorry about that. Okay, so the rest of them are down here. Faster than light travel, hyperbola. That's what it's a technology-oriented space flight blog by flight's technical reporter Rob Coppinger. I googled the hyperbola neutrinos to see what would come up, and this book came up. Neutrinos in particular, particle physics, astrophysics, and cosmology. It's by F.J. Paul Solar, and it's a brand new book. I believe he just brought it out in 2011. Represent the neutrino hyperbolas defined in EQ2 for muon kinetic energy. TU equals M250 ME and 3 muon angles. Okay, so that came up. Again, there's another link there. That's a PDF. Usually if it's a PDF, it's a thesis, a theory, or a new invention that's been created. So that was posted November 2011, so it's brand new stuff. Next was the conservation of momentum. It's a mathematical consequence of the homogeneity shifts symmetry of space. Position in space is the canonical conjugate quantity to momentum. It's a concept of physics along with the conservation of energy and conservation of mass. And so I looked it up even more to find out what is it. And here's a chart or a diagram. It says initial momentum equals 0, equals final momentum equals P muon and P neutrino. So they have equal momenta in opposite directions, of course. Let's just call it P. Conservations of energy. In natural, C equals 1 units. Initial energy is M pion equals final energy equals P plus SQ. RT is M muon. Okay, I don't know. These are mathematical equations that come up there. The kinetic energy of the muon is its energy less its rest energy. Okay, so these are, I found that at answers.yahoo.com under questions. Okay. I don't know what the original question was. I think it was about muons, the speed of muons. What is the kinetic energy of the muon? And I found that on Yahoo. Okay, so I'll put that link on there for you to look. And so then the pion muon neutrino comes the rest at rest decays into a muon. A pion at rest decays into a muon, and a neutrino. Find the kinetic energy and the momentum of the muon and the neutrino. So that's under kinetic energy. Michael A. Gottlieb, Introduction in Feynman's Tips on Physics, a supplement to the Feynman Lectures on Physics by Richard P. Feynman, Michael A. Gottlieb, and Ralph Leighton, Addison Wesley, 2005. That's from www.feynmanlectures.info. I'll be posting that link on the website. The OPAL experiment at LEP 1989-2000, this came up. Actually, this picture came up with the original document where I found out about neutrinos possibly going faster than the speed of light. So I went to the website and I found this picture, and then of course I had to Google OPAL because I didn't know what it was. And I was surprised to see that OPAL is a test that is from CERN, and at CERN's come up in other videos, and I thought it was a computer language. I didn't know it was an actual testing facility for neutrinos. So CERN came up at the beginning with Perl, and I thought it was a program, a computer program. Then I found out now it's a testing facility for neutrinos, and neutrinos travel faster than the at CERN, they made the particles travel faster than the speed of light. That's where they did the test, and they managed to do that. Okay, so this is an older program that they were doing. It ended in the year 2000. But obviously the data is important because it did come up with this. So OPAL was one of the major particle physics experiments at CERN. OPAL studied particles that their interactions by collecting and analyzing electron positron collisions events at LEP. Oh, you know what? The new one's called OPERA, O-P-E-R-A. So all they did was change a couple of the letters. So if you look up OPERA, O-P-E-R-A, that's the newest name for the newest test for the neutrinos. The Large Electron Position Collider, LEP, was the largest particle accelerator in the world. So it accelerates these particles to help them travel faster. There were 3 other experiments at LEP, ALEPH, DELPHI, and L3. You can take an interactive tour of the particle adventure, or you can be a particle detective, identifying interesting particle physics interactions taken by OPAL. So they have this fun little website you can go to, opal.web.cern.ch/OPAL. Okay, and there's the test that they're doing. This event shows the annihilation of an electron and a positron. In this interaction, a pair of heavy charged particles, W plus and W minus, bosons, is produced. Each of them decays into 2 quarks, which are finally detectable as particle jets. Rotating view. I better go back up here before I get lost here. Okay, in a terse, peremptory sounding paper posted online on September 29th, I believe that was 2011, Andrew Cohen and Sheldon Glashow of Boston University calculated that any neutrinos traveling faster than light would radiate energy away, leaving a wake of slower particles analogous to the sonic boom of a supersonic fighter jet. Their findings cast doubt on the veracity of measurements recently announced at CERN and posted online here that clock neutrinos going a sliver faster than light. So blogs.scientificaamerican.com. Degrees of freedom, superluminal neutrinos would wimp out en route. That's what that article is about. The result announced at CERN on September 23rd, I believe this is 2011. Although the news had leaked out ahead of time, it was certainly unexpected. By now, if you haven't heard of it, you must have been a straggler from the Imperial Japanese Army coming out of Iwama-jima's tunnels. Anyway, to recap, the war in the Pacific is over, and a team of physicists has released data on neutrinos they beamed through the Earth's crust. From Geneva to Gran Sasso Massif near Rome, so Geneva I believe is in Switzerland, in an experiment known as ALEPH. According to the physicists' estimates, the neutrinos arrived at destination around 60 nanoseconds too fast, violating the cosmic speed limit set by Albert Einstein's theory of relativity. Okay, so that's where it came up. And then we'll go over this way, down here. Now this is the OPAL detector. That's what it looked like. You can look there and it shows you a diagram of what it's about. And it's, okay, so the OPAL detector, the OPAL experiment and the LEP collider started operation in 1989. Data taking finally ended on November 2nd, 2000. The OPAL detector was a large multi-purpose particle detector, so that was 12 years ago. The detector was sited on LEP acceleration at CERN and measured the results of interactions between electrons and positrons which collided at the center of the detector. The incoming electrons and positrons approached the center of the detector from opposite directions along the beam pipe. The beam pipe was an excavated straight metal cylinder of a few centimeter radius. Passing right through the middle of OPAL, it provides a natural axis of symmetry to the detector. The components of the detector were arranged outside the beam pipe in a layered structure, rather like the layers of an onion. Okay, so the detector is 12 meters long, 12 meters high, and 12 meters wide. And I'm running out of battery power again. So I'll probably finish doing my thoughts for 16b in